thanks so much everybody for joining our online teach-in on energy storage. My name is Betta Broad and I work on New Yorkers for Clean Power, a statewide campaign to accelerate the transition to clean energy, which includes renewable energy, energy efficiency, and electric vehicles. And this is the first time that we've had one of our online teach-ins focusing on storage, but it's a super important topic and necessary if we are going to run the world on renewables, which we plan to. And I just want to say a special thank you to Manna Jo Green, who often comes up with fantastic ideas, and it was at Manna's direction that we bring the gang back together because we had a really terrific storage seminar or session at our Climate Solutions Summit this past fall. And so we were talking about this initiative that we're working on, the Regional Renewable Implementation Plan, which we can talk about some other time, but it's a great effort to transition the Hudson Valley to renewable energy, and of course storage would be critical in that. And so we decided, let's see if our speakers from the fall would be willing to come back and reprise their presentations. And we also invited Erin Hazen, who did a fantastic job on another online teach-in that we did a couple of weeks ago together. So just want to thank you all for being here and for our speakers for coming back and being a part of this. It's a super important topic, and of course I hope everybody at home is doing well and staying safe and staying healthy, and appreciate you being here as we continue to do what we can to move the needle in the transition to renewable energy. So yes, thanks for being here. Hope you'll stay to the end for our Q&A. Keep the questions coming in the middle bar. And I will pass it off to my wonderful colleague, Michaela Shavacco, to introduce the speakers. Michaela?
Thanks, Betta. Hi, everyone. I'm Michaela Shavacco. I'm the program coordinator at New Yorkers for Clean Power. Looking forward to this teach-in on storage since I missed the presentation at our Climate Solutions Summit this past fall. And I'll be sure to take careful notes for our coming soon energy storage page on our New Yorkers for Clean Power website. So to start us off, we have Tom Kacandes, the Business Development Manager for New York and New England at VEIC.org, giving us the basics on energy storage. Then we have Erin Hazen, Senior Director of Development at Glidepath Power, describing the commercial uses for energy storage. Jeff Irish, the Vice President of SunCommon, describing the residential uses for storage, and Candace Rossi, the Program Manager for Clean Energy Siting at NYSERDA, explaining the opportunities for incentives and funding for commercial and residential storage systems. So thanks again, everyone, for joining, and I'll hand it off to Tom to explain some of the basics of energy storage.
Thanks very much, Michaela. You can hear me okay, right?
Yes.
Okay, so we're going to breeze through a very basic review of some of the considerations that attach to solar plus storage. Very briefly, I work for a not-for-profit of 3 decades standing. We function as the NYSERDA of Vermont and Washington, D.C. We do incentives administration and things like that for parts of the Midwest. We consult on energy for Hawaii and other folks around the world. But relative to solar and storage, we're going to speak at a basic level about how it works. What is it? What happens when you change from a grid-connected system to a system that integrates energy storage? And then I'm going to just wave at some of the larger scale topics, which Erin will be able to expand on for us. So we have a climate emergency. Let's talk about this piece of solving that. Everybody uses electricity, but me included, we understand a certain amount about it. we know how to use it, we know how to plug things in, and we might know that there are two basic flavors of electricity: direct current, because we all use batteries of different kinds, even if they're just AA cells, those are direct current. Solar panels are also direct current. But early on in the quote unquote current wars, we found that alternating current had some advantages for transmitting over long distances. And New York State was actually the place where the first electric grid was built. So this is a view of how the voltage of electricity gets changed, and parts and pieces make up the grid. They consume some of the energy that ultimately gets to us. And we have this DC-AC division. So here's an actual photo of a substation. It's designed for taking high voltage transmission and bringing it out to a distribution level and applying some controls for a small area relatively. And because it's easier to transmit high voltage over long distances, that's what tends to happen on the big power wires you're used to seeing. And then the low voltage and smaller amounts that we see go over what we call the distribution system. But electric current is at least 60 times a second in flux. And what we use and the load that we put at our houses and collectively on the grid causes the grid to flex and respond. And when we create islanded systems, when we are our own grid, living off of a battery, these same dynamics apply. So it's just good to understand that some power is consumed. There are a lot of dynamics to power. Reactive power is an important one that I like to just clue people into the fact that when you turn motors on and off, and this is especially true of high efficiency induction motors like those involved in air conditioning, it creates a demand on the grid when that motor first turns on in particular. We're all familiar with the idea of solar, but what is it really? I mean, there's energy that comes from the sun across a whole spectrum, solar cell technology of different types, and yeah, we've sort of standardized on what the typical solar panel is, but at the physics level, we're taking some portion of useful life and converting it into direct current. And then if we need more direct current, we can connect solar panels in series, just like batteries in a flashlight. And when we talk about energy storage at the larger scale, well, now we're starting to see lithium-ion batteries and cordless drill power pack, and we're used to lead acid batteries in cars, and they can be used for stationary applications. But when we start thinking about the most recent developments, we're often looking at ganging together lots and lots of small cells. This is all very understandable. You just haven't spent as much time thinking about it as maybe some of our speakers. You put together, build up voltage, and that can happen even at the grid scale. So now we know there's lots of little batteries in that little Tesla box, and it's a pretty box, but there's lots of different boxes, and they come in all different sizes. Think about the house that this system is in as a set of demands on electricity, and that battery and solar working together to respond to that. And that makes the common thing that I heard when I was involved mostly with residential folks having the conversation, they'd say, I want to get off the grid. Oftentimes, we're not really talking about getting off the grid. We're talking about supplying some of our own energy in an intelligent way. It could be grid tied, it could be grid tied with a battery, could be living off of the battery, in which case we have to really drill down and think about what I'm calling loads, all of the things that demand electricity. And they demand AC electricity, and the AC comes from an inverter, which has a certain capacity. Battery has a different capacity. So when are different things turning on, even in the course of a day? Do we have a pool? Pools are lovely. They use a lot of electricity. At the commercial and industrial scale, again, what we're really talking about, look at this battery pack here on the lower left. This is just one example system technology that I did some work with, the company that brought this forward. It's lots of little batteries in a big box. So if we're now talking about, as Candace will tell us, bringing batteries across New York State, here's a building where I built solar. This happens to be Bread Alone in Ulster, New York. Where would we put a battery here? Would it be inside the building, outside the building? How would it be connected to the building? What loads would we be trying to manage with that battery? Are we trying to store the solar? So we have to look at what our load is. This is an analysis I did for a different customer. We have to look at how much solar we might have. Maybe we don't have any solar. We can do energy storage with or without solar. They're just both sources of DC. And then we have to look at where we can put the battery, meeting regulations, fire regulations, among others. And then how are we financing a project? So here's a review. Where would we put the battery? How much solar might we have? And then what is the building's demand when we add up all the motors and all the lights inside that building? This particular customer on a Sunday when not a lot of employees were there was 80,000 watts of demand at any given moment. But in the middle of the summer with all the AC cranking and lots of people in there sweating, they would hit 270,000 watts. That's what kW is. And then if we have an inverter that's supplying that AC and it has a capacity of 250 kW, this relationship of peak and low demand to the capacity of the inverter is a feature of us supporting load. But then we have to look at the energy storage capacity. And if the storage system capacity is the maximum of the inverter times 2, that gives us 2 hours. If we have solar as an input, how much full-on solar recharges that battery? So now we have a set of concerns that need to be viewed. I wanted to just mention that our client, Hawaii Electric, has done some early work in virtual power plants. We can gang together small batteries and control them over the internet and other systems. And this kind of speaks to a commercial overlay to the type of residential system that Jeff's going to cover. And then finally, as we integrate, whether it's a house or the school in your town, multiple schools, now we're going to be plugging in electric cars and electric buses, and we want to work with the grid. We don't want to create a brand new taxing demand on the grid. We want to work with the grid, and stationary energy storage is one way that we can avoid causing issues. So it's important for us to look at the grid benefiting from energy storage, for us looking at managing our demand, and for each of us to answer this question: how do we use electricity? What could we do to live off a battery, even if we're not exclusively living off of a battery? I'll leave it there. Thanks so much.
Thank you, Tom. And we'll pass it off to Erin to describe some of the commercial uses for storage.
Great, thank you. All right. Okay, so Tom touched on a lot of really interesting information, and a lot of what I'll present ties well into that. My company, Glidepath, operates and operates, develops utility scale energy storage, sometimes paired with solar or wind, but a lot of our systems are standalone. So let's look at how storage fits on the grid, kind of, take a step up in level from the residential and C&I scale. One of the challenges with storage from a, both a community education standpoint, but also finding the markets for it and financing for it is that storage can fill many different roles. So defining storage is important. Defining the use case for a given project is really important before you put a lot of work into advancing that project. So storage can be connected to the grid at the transmission level, high voltage type substations, distribution level, which is more the medium voltage that goes through your neighborhood, it serves industrial parks, or behind the meter at directly on the customer site. Behind the meter installation directly benefits the customer, can provide services such as backup power if there is a grid outage. A lot of hospitals and other critical facilities are looking for that backup power. It also lets you increase your renewable consumption. So you can store the excess solar that you are generating perhaps during the day when everyone's at work and in normal times, and not using as much electricity, and then come home at night and then you can use that solar rather than letting it just go to waste or go to the grid. You can reduce your demand charges, so you can help shave that peak of your usage, and that really has a major impact, especially for industrial users. And you can manage time of use. Many customers, larger customers especially, and in other regulatory regimes, their price depends on what time of day it is. So you can make sure you're applying your storage during the times of highest prices, and that way lower your overall bills. The utility scale storage is where I operate. We're in the multi-megawatt size projects. I've developed, we've got 4 construction-ready projects in New York. They're all 20 megawatts, and they are 4 or 6 hour duration batteries. And those are typically installed at the, like I said, the distribution level voltage. We look at that medium voltage. Typically your transformer costs are not as expensive as if you were trying to attach to the grid at a very high voltage. So a lot of our interconnections are in the 13,000 range voltage. One of the things that's important to understand is that it's not necessary to co-locate these with renewables. They benefit renewable energy even when they are standalone, far distant from those projects. This graph on the right shows some of the many functions of energy storage. I've gone through a few of them, and point out that frequency regulation over here. We'll talk a little bit more about that in the next slide, as well as deferring transmission lines and spinning reserves. So that frequency regulation, if you recall, Tom mentioned our grid operates at 60 hertz. Well, when it gets out of that range, that causes a lot of problems. And it can even cause the grid to collapse and have a major blackout. So battery storage can help prop up the grid when there is a frequency issue. That's called frequency regulation. And you mentioned inductive power, that major motors and factories and even our transmission lines themselves, they require power before they can operate. So batteries can provide some of that. That's called black start services. If there's an outage, batteries can be the source of that initial inductive power. Okay, and as I mentioned, it does benefit renewables quite a bit. I've highlighted the various functions that are most relevant to how they can support New York's expansion of renewables. I believe, Candace will go on at the end of this presentation a bit about your goals in New York, and storage is really integral to those goals. It will help support that rapid build out of wind, solar, onshore and offshore wind. Okay, here's where I get a little wonky. We're gonna spend a little time going through this. This is a snapshot actually of a day in the life in California, where they have quite large renewables penetration in their grid. New York is on its way there. You're not there yet. The blue line is load or electric demand. So this is what everyone's using during the course of the day. And this curve is fairly typical in most areas. You have a very sharp ramp up in the morning. Things are level and a little bit lower during the afternoon. And then when everyone gets home from work, everyone fires up their dishwashers and air conditioners. And, we just really see a huge steep ramp up there. The yellow line is solar. Solar, as you can see, is on a good sunny day. It's fairly steady and predictable demand during daylight hours, but it is an extraordinarily sharp ramp up and ramp down. Wind, on the other hand, is very lumpy. It's much more variable. It's prone to kind of sharp increases and stalls, and it's less predictable throughout the day. Industry and we're making advances in predicting wind better, but it remains a challenge. So all of these are, they're legitimate challenges for grid operators. It is not easy to balance these variable inputs of generation with variable load, and the grid really needs to stay in balance. So we have times where solar generation may exceed demand. Actually, there's more solar output during that midday period than the grid actually needs. And with wind, you have this, very variable generation. It's lumpy. It's and again, the grid has to stay balanced. So some other source of generation or load, a customer may need to dial back, their curtailment agreements out there. So anyway, someone has to react to all these bumps. It can't just be left that way. So here's where solar can help. So where we've got, here's some of the additional problems. Like I mentioned, when you have excess generation, it just goes to waste. It can be through curtailment, where generators are dialed back and said, you know what, you can't generate right now. We don't need the power. Or you could see it in the form of negative prices on the market. So it's worth more to the generator to just keep running and pay someone to take that power. Obviously, that's not the best business model. And you have these sharp demand increases. And right now, those are covered by peaker plants, fossil fuel-fired peaker plants that are typically our least efficient generators on the system. They're our most expensive to run. So they only run short term like this. Picture drag racing with a semi. That's pretty much what it's like, so it's gunning full bore to catch up to this peak. And that's, the whole time you can imagine the emissions and the water use, and it's just not an efficient way to generate power, but it's necessary. It's the tool we've had. And then finally, you have this frequency regulation, and that's handled currently on the grid by ramping up and ramping down existing online generation sources. Again, that's not an efficient way to run. And when we think about efficiency in generation, think about fuel usage. So we're wasting fuel when we run inefficiently. So again, these are real challenges for grid operators. You hear a lot of utilities, kind of a counterpoint to renewables saying, hang on, we can't integrate all these renewables. They're not just crying wolf, it's hard. And the existing fleet really has to work harder to do that. So one of the things storage can do. So we can use long duration batteries here and shift whole hours worth of generation for later use. Okay, so it's a different kind of battery, maybe a different chemistry than what you would use for, oops, I went back too far, than what we'd use in this situation, which is shorter duration batteries and fast cycling batteries. Okay, so the goal is to make that renewable generation more predictable. It makes that base load generation more efficient because it can rely on a steady stream of power from these renewables. You can shift this whole chunk of demand, or rather a generation, to meet this chunk of demand. And that reduces the strain on the grid. It may help defer the construction of new power plants, new transmission lines, et cetera. So there's a lot of really huge benefits to that, shaving that peak. And it also helps reduce the need for peaker plants. And then finally, all of these changes help lower the bulk system costs. So yes, there is a cost to this transformation of the grid, but over time, there's a huge benefit to the economy, to the ratepayers' economy. In Texas, they found that study just came out late last year. widespread integration of distributed energy resources such as solar and storage will save them billions and billions of dollars just over 10 years. So takeaways, it's important to understand energy storage is, for all these reasons, energy storage is backed by most of the leading environmental advocacy organizations. It fills the role of peaker plants without emissions, water use, fossil fuel consumption. It will help stabilize our grid and make it more resilient. That extends the life of the existing resources we have, and the greenest power plant we have is the one we don't have to build. It's an enabling technology for wind and solar. So as New York increases dramatically its wind and solar generation on the grid, storage is really essential to help smooth that path. It's safe technology, and it will be, as I said, central to that transformation of your grid. That is all I have.
Thank you, Erin. Thanks for that overview of large-scale uses of energy storage, and I'll pass it off to Jeff to describe more of the residential uses of storage.
Okay. Good afternoon, everybody. Are you seeing that?
No, not yet.
Michaela, are you seeing my screen?
No.
Okay,
Nope, not yet.
try that again.
I think we have your slides, Jeff, so we could share. Mick, can you share your screen, or should I get them up? Do you have them handy?
I think it might be coming now.
Oh, now we got it.
There we
All
go.
right. Woo! Got it.
There we
Terrific.
go. All right, good afternoon, everybody. My name's Jeff Irish. I'm with SunCommon. I started a company called Hudson Solar almost 20 years ago now, and we merged with SunCommon, B Corp, a couple years ago, and I now run our New York business and operations here. SunCommon, the rest of it is up where Tom is based out of Vermont. I'm going to talk about storage for residential and small commercial applications. There's been a lot of developments in the last few years, and I'm going to start with where solar and storage was over the last 2 decades. Solar being coupled with storage is not new. We did our first system back in 2005. We had a large grid outage in the Northeast back then, if everyone remembers, and it was in August. It took out most of the Northeastern United States and Ontario. And my wife at the time said, well, we have a solar system, so we ought to be okay. And the answer was no, we weren't, because all solar systems are required by federal regulations for safety to disconnect from the grid when the grid goes down. And the reason for that is that if they didn't disconnect and if they continued to supply power into the grid, it would be a safety hazard for utility personnel that are out there trying to fix the outages. So they all automatically disconnect in just a fraction of a second. So it requires special equipment to have a solar system and make it work when the grid goes down, and that's a battery system. This is the way the systems looked like for about 13 years as we designed and installed them in the Hudson Valley. They consisted of a battery box, pretty rudimentary. Here we are actually using a plastic garden box to store the batteries in. I'll show you what's inside that box in the next slide. There's a lot of equipment that went along with the system, the battery inverter and switch gear, which would make it work when the grid went down. And then there was a small panel over to the right with a bunch of buttons on it, which was the control system that we were always hoping that the homeowner wouldn't play with. So, but that's how they worked. Inside that battery box, it looked like this. There were, in our typical systems, about 1,500 pounds of sealed lead acid batteries. Sealed, meaning they were maintenance free. You didn't need to add electrolyte or solution to them every month like you do with flooded batteries. So they're pretty safe and pretty reliable, but there was a lot of them and they were big. 1,500 pounds is a lot of batteries, and we were also limited in the technology that you couldn't really put many more batteries together than the 8 you see here. You could maybe go up to 12, but that was about it. But these systems worked. They worked really well. They provided, and they continued to provide, automatic, fast, silent, rechargeable backup of critical loads when the grid goes out. It's so fast, it's so silent. When the grid goes out, you typically don't even notice, especially in the middle of the night. You don't hear a generator come on. The grid can come back on and you may not even notice that you had an outage. A system like the one I showed would contain about 12 kilowatt hours of usable energy in its first year, and that's about half of what a home would use in a day, your average home. And I say in the first year, that's because the lead acid technology would degrade as soon as it started to be used. What we would tell people is that the lifetime of the system was about 10 to 14 years. And at that time, the system would probably still work, but the batteries would only have half the capacity that they originally had. These systems were not cheap. They cost about $25,000 at the time. There was no real warranty on the batteries. And that's because if the homeowner played with that little control box on the side, they could destroy the batteries in a matter of an hour or so. So they didn't really come with a warranty. But as I said earlier, they worked. These systems still work. We have one at our shop. I have one in my house. And they continue to work, and they work very reliably. Over the time in the Hudson Valley, over those 13 years, we installed about 80 of these systems out of a total of about 1,600 solar systems, residential solar systems that we did. So about 5%, 1 in 20 of our customers was interested in getting battery backup with their solar system. There've been a lot of changes. This is what they look like today. We're designing and installing systems from Tesla now, the Powerwall. We're a certified installer with them, and they've shrunk in size, they look a lot better, and they're a lot more powerful than they used to be. The control is moved off of that box that's on the wall, and it's now on your phone. You have smartphone control, can show both real-time situation, the real-time power flow, which is on the left there, where you can see that the home is essentially running off of solar, and solar is generating 4 kilowatts. The Powerwall battery is consuming 1 kilowatt to recharge itself, and the loads in the home are running with 3 kilowatts, and they're not using anything from the grid. And then you've also got data monitoring on the right. This is very similar to what Erin showed as far as the daily load profile, except she was showing what, say, the state of California might see. This is what your home might see, but it's very similar, that your load, the load profile through the day. But you've got the data monitoring and you've got the data logging all on a smartphone. So what's happened in just the last few years is pretty phenomenal when it comes to residential and small commercial storage. We've now got the same power and energy, but it's now expandable. A single unit is about 1/4 of the size of what that old battery box was. It weighs about 80% less. It costs about half of what that battery system cost, and it has a lifetime of at least 5 times what the older systems, the lead acid systems were. All of these changes are coming to us courtesy of the electric vehicle industry. That's what's driving the technology. That's what's driving the economies of scale, and that's what's driving the cost down. So systems today, they're still automatic, fast, silent. They recharge from the sun. Tesla Powerwalls and many other residential battery systems are stackable. The Powerwall, you can stack from 1 up to 8 to 10, which can give you up to about 100 kilowatt hours of usable energy storage. That's equivalent to anywhere again from half a day of household load up to about 4 days for your average household. The warranty now is real. It's 10 years, and that assumes that you do full discharge and recharge every day for 10 years. That's how reliable the products have become. The systems start at about $15,000 in New York State. We have some pretty onerous utility and building permits, local permitting that we have to deal with, which adds some cost that's not apparent in some other locations, such as Vermont. As I said, smartphone monitoring and control exists, and we've installed about 400 of these systems. We're finding now that about 20 to 40% of our customers that have solar want a battery with it. There's also some really exciting new applications. Again, some of these are very similar to what Erin talked about at the grid level. Battery backup is still there. We used to only be able to back up critical loads, but now since we can stack batteries, we can do whole house backups by just stacking power walls together. There's also a new application called self-powered, where again, as Erin mentioned, you can do it at the household level too. You can store your energy, solar energy that's produced during the day, and use it after sunset. There's time of use that's possible. So if we're in a utility area where they charge more for midday power than nighttime power, you can shift your use and not use any of the expensive daytime power and only use nighttime power. Products like the Powerwall are now capable of operating an off-grid operation and applications. So if there's remote cabins or things where there's high grid connection costs, you can now go off-grid pretty easily and reliably. And then there are some commercial applications such as peak load reduction, reducing demand charges for small commercial customers, and fleet utility control, where a network of power walls, such as applied in Vermont, are actually under partial utility control, and they can draw on those household batteries during peak load events in order to reduce the peak load that they have to, or peak electricity that they have to go purchase from outside. And this is kind of what it looks like. The control's gotten pretty easy. You can control it and change its configuration with a smartphone. You can select backup only. I've got our building unit here now in self-powered mode, where I've said that we're going to try to run off the sun for a while until the battery gets down to 50% capacity, and I'm reserving 50% in case we have an outage. Advanced, we could go to time-based control to exploit time of use tariffs. When the utilities implement those, they become more widespread. And then you've got some pretty interesting applications, artificial intelligence applications like Storm Watch, which I've got selected here, so that if a storm was coming, the system controller is looking at the weather and will probably not take me down to 50% battery capacity, because it knows that I might need more than that for when a storm comes, if the power goes out. Do we have outages? I found this pretty interesting. Just in the last 9 months, it looks like we've had 7 outages at our facility in Rhinebeck. Some of them are only for 5 minutes, 6 minutes, but then, you know, there's one up there almost 10 hours, another one 2.5 hours. So outages continue to happen. It's not always bad weather. Sometimes it's cars hit telephone poles. The utility needs to change some of their equipment around. There's lots of reasons for it. And then last chart here, showing what happens in self-powered mode. So this was actually a couple days ago, what was going on with our system. Our rooftop solar was producing power, charging the Powerwall, running the rest of the building, and we weren't using anything from the grid. So there's been a lot of advances in the last few years, and I think it's a really exciting time for residential battery storage with solar.
Yeah, thank you, Jeff. That does sound all very exciting. And so just quickly want to pass it off to Candace to explain some of the opportunities for incentives and funding for large scale and smaller scale battery storage.
Yeah, great. Thank you. My name is Candace Rossi and I work at NYSERDA. I work on both the clean energy siting team and the New York Sun team. But today I'll be mostly talking about the state goals, what we're trying to do with energy storage, and our resources we have available for local governments across the state. So as you might be aware, New York State has pretty ambitious storage goals and energy goals in general. We're working to be 70% carbon-free by 2030 and 100% carbon-free by 2040. We have many different renewable energy programs that are happening to help get us there, but storage is definitely going to need to be installed to complement all of these assets. So storage is a main component to help us to get to the goal that we need to reach. So last year we had released our energy storage initiative. We have a goal to meet 1,500 megawatts of storage by 2025, and then get 3,000 megawatts of storage by 2030. We currently have an incentive program that is available. We have retail incentives for commercial and non-residential programs and projects. We currently have the New York City incentives are still open, as well as we have a Con Edison Westchester block for incentives, and Long Island, which are still open. We've actually had an enormous amount of uptake for what we call the rest of state for these larger commercial projects. So the incentive blocks for those projects are currently fully allocated. And then we also have open incentives for residential projects on Long Island. So those are kind of the retail incentives is what we call them. And then we have another incentive for storage, which is called the bulk incentive program. So these are for the larger projects and over 5 megawatts. So those are usually dealing within the wholesale market. Now, for us to meet all of these goals that we want to hit, we need to provide technical assistance to our local jurisdictions that are managing these projects. So this is really where our team comes in, of the clean energy siting team. So about 2 or 3 years ago, NYSERDA created the clean energy siting team. And our main goal was to work with local governments, originally on solar, to help them manage these developments that were happening in their jurisdiction. We initially created the New York Solar Guidebook to help. So this is a collection of tools and resources that jurisdictions across the state can use and implement to help manage these projects. The guidebook was probably 4 to 5 chapters, and I think now it's up to 12 chapters, ranging from property taxes and payment in lieu of taxes, as well as sections on seeker. One of our more popular sections is the model law, which is an all-inclusive resource for towns to look at while they're kind of adopting their laws around solar. And basically, New York State is a home rule state with 1,600 different jurisdictions, which means the potential for 1,600 different ways to have these projects permitted. So we want to get out there and make sure we had a model that these towns could use, make their own, and kind of create these permitting process. So with the success that we had with the solar guidebook, we released the battery energy storage guidebook last year. So this guidebook has a model law to create kind of the permitting process, so how these projects will be permitted in your jurisdiction. Additionally, we have a model permit and inspection checklist, and currently what is 2019 energy storage supplement. So similar to the solar guidebook and the storage guidebook, we don't anticipate jurisdictions just to pick up this book and become an expert on these technologies. We know they're new. A lot of towns haven't seen this before. So we also provide technical assistance. So we will either work with a town one-on-one to help with any questions they may have regarding these kind of developments in their jurisdiction. Additionally, we host workshops across the state. In the past year, we've held around 25 battery storage workshops on county level across the state. So we've really worked to put resources that can be used by towns, and then we're there to help them walk them through and kind of get them to the next step. Something I want to highlight is the 2019 energy storage supplement. So this was incorporated into the New York State Uniform Code as of July 1st, 2019. Originally, New York State had codes for battery energy storage based on the 2015 code cycle. But as we're kind of helping deploy these projects across the state, we want to ensure that they're being installed safely and correctly. So we actually worked with the Department of State to skip 2 code cycles and amend the current code. So instead of being based on the 2015, we actually skipped to what is the 2021 code, which has been incorporated and since July, and no local town needs to adopt this. This is across the board in New York State. And this just added more provisions related to the installation, use, and maintenance of energy storage systems. So we just wanted to make sure that every one of these systems are being installed are being done so safely. So this has actually been implemented fully into the 2020 New York State Uniform Code, which is effective today. So if anyone didn't know, we had a code cycle changeover today. So nothing in the supplement changed during this code changeover. It's just been fully incorporated. And here's just the announcement saying how it's been updated. And lastly, this is our Clean Energy Siting homepage, and this is how you can get in contact with anyone on our team. Basically, you could get all of our guidebooks that we have available, and then also you can request technical assistance by emailing us at cleanenergyhelp@nyserda.my.gov. And that's what I have, but I would like to encourage everyone on this webinar as kind of a takeaway to reach out to your local jurisdictions that you might be working with who might be having issues or are permitting these projects for the first time. I would really encourage them to come look at our energy storage guidebook, our webpage, and reach out to us for any technical assistance or questions that they may have. All right, thank you.
Great. Thank you so much, Candace, and everybody. Terrific presentations. Learned a lot. The first time you all presented at our Climate Solutions Summit, it was, I think, the last session of the day, and I was completely spent at that point. So it was great to get to see your presentations again. And Erin, terrific addition to the team here. So let's just dive in. We've got tons of great questions. I will kick it off with this one. Given the challenges with determining a fair value for solar energy placed on the grid, how difficult is it to determine a fair value for energy storage, particularly for storage solutions that provide grid services like voltage regulation? Have any states figured this out? I'm not sure who would make the most sense to take that one on. I don't know, Erin or Tom, you want to take a crack at it?
Yeah, I'll start and Tom jump in. Have any states figured it out? Well, it is a tough nut to crack, but there are existing market mechanisms for what are called these ancillary services that storage can provide. So voltage support, frequency regulation, black start. Those are all established services that are compensated in the markets currently. So like a peaker plant, for example, that would be kept online, like today, kept online all day long just in case they're needed. They're compensated to do that. So storage can participate in those same markets at the grid scale.
Yeah, I don't know that I have a ton to add, except that in general, we are looking at a real need for tariff reform and the capabilities that batteries offer and energy storage generally to be acknowledged financially. And it's been said that the electric grid in all of its parts and pieces is the most complicated machine ever built in North America. And it certainly is the most complicated market that I've ever studied when you try to figure out who's paying for what and when. And I mean, we have a team of 6 people who basically just do that. So I like to talk to them. I nod. I do not understand everything that they understand. It's really complicated. But one of the really big differences and potential values that I want folks to be encouraged about is that in my talk, I kind of pointed out the almost magical and constantly changing physics that are acting on the grid and all of the interactions happening across the grid. Well, it all happens within a range and it mostly works. In Germany, the grid is regulated differently than it is here. And if you go to people and say, hey, don't you want a generator for when your power goes out? They don't know what you're talking about. They don't lose power 8 times in a month. It just doesn't happen. And some of the German manufacturers involved in energy storage aren't really looking at Germany to sell their stuff primarily. So batteries, in their ability to respond instantaneously, I mean, remember, we use batteries for improving the quality of power so that computers don't lose a fraction of a second of perfect power and a bunch of data is lost. Those are called uninterruptible power supplies. They're battery storage for banks and important computers. So the ability of stationary energy storage to respond faster than traditional generation is a big deal. And in a whole bunch of markets, that value is not acknowledged. You know, it comes to the window on which you value a response. And if that window is 15 minutes, a natural gas plant can maybe spin up a generator, but a battery can respond in a couple of hertz, correct and support a condition, and then pop back off. Traditional generation can't even do that. Otherwise, we'd have little generators supporting the computers at the bank, and that's not what they use.
I just want to add one thing too about whether states are recognizing or understanding how to value it. There are also some threats to storage and renewables in general that are happening right now at the FERC level, the federal level. So I would encourage listeners on this call to, there's a couple of actions in New York. FERC issued some orders that it's called buyer side mitigation. You know, it gets really complicated. I won't go into all the technical reasons, but there are ways that politically appointed folks at the federal level are undermining the great policies that states like New York have implemented. So that is on the kind of negative side. There are some threats out there that, you know, I encourage you to look at and get active about.
Thanks, Erin. Maybe we can even share a link to an article or more information about that in our follow-up email to folks, because it is important to keep our eye on FERC. And also a reminder of why it's so important to have elected officials in office who support renewables. But I don't need to tell any of you that, not with this group. So yeah, super complicated topic and one we could delve a lot more into, and we've got some great questions. I do want to just recommend a good book that talks more about this whole issue, which some of you may have read, The Grid by Gretchen Bakke is quite good, I thought, with explaining more about how the grid works. Okay, so question from you all. What are the components of these backup batteries? I think, Jeff, you kind of touched on that with your explanation, but I don't know if anybody wants to get into that a little bit more.
Yeah, almost all the batteries now, except for some of the specialized applications Erin mentioned, are lithium ion. So in the case of the Tesla Powerwalls, it's the same battery cells that are in their cars. And then another key component, though, is the battery management system. Lithium ion batteries require a sophisticated battery management system to prevent them from doing things like overheating and having problems. So typically, if I think someone else asked about fires, there have been some fires with lithium ion battery systems, and they typically were caused by failures in the battery management system. the electronics that control how rapidly the batteries can discharge.
And well, while we're on the subject of safety, we have another question about the whole issue of battery storage facilities impacting environmentally sensitive areas. The question is particularly regarding corrosive chemicals that can contaminate the area, that people are more worried about that when it comes to batteries versus, say, electric lines over wetlands and aquifers. And just hoping that some of our speakers could comment on those concerns. I don't know, Candace, you probably deal with that a lot with working with communities and concerns with permitting storage projects. If you and Erin want to chime in, maybe.
Yeah, I can give a quick response. Kind of also with us moving to the code cycle that we're on now that is more stringent than previously was in place, there is more requirements within the code to make sure that for the batteries that do have anything corrosive, that there is a containment system in place that ideally won't allow for that to happen. So there's a lot of different parts of the code that is now in place that will basically be more protective for these batteries that are being installed. Additionally, I would encourage if any towns or whomever have some more specific things that they're more concerned about to look into our model law that we have for battery energy storage to make sure, you know, those specific things that are really important to their community are being hit to ensure they're not happening. But I am pretty confident in the latest code that's been put out there that a lot of these risks will be mitigated.
Yeah, I'd love to add to that. The utility grade battery systems that are commercially available that we choose and all the established developers are using are exceptionally safe. There's redundant layers of protections built in, starting with first UL codes and standards that everything is manufactured to. They have very durable packaging that's resistant to puncture or tear or any other abuse. Each of these containers, these individual packets, is limited to about 100 milliliters of an electrolyte gel. That gel is not a free-flowing liquid. It's not something that would leak. I think a lot of people picture batteries and that old lead acid battery that might be in your garage for 20 years, right? These are nothing like that. There's secondary containment provided by a module case that surrounds the cells. And this is made of steel or rigid plastic that would contain if there were some kind of failure. And then there's usually tertiary containment as well, so spill absorbent mats or booms within a container. And then finally, these battery management systems you've heard us talk about, they are monitored 24/7. You can drill down to the individual cell level in any given facility, and it would pick up changes that would be caused by a leak. So state of charge, voltage drops, short circuits. At the very minute level, the BMS management system picks up those changes and would flag an alert condition so it could be intervened. So the risk is exceptionally low. You know, for example, these batteries, these lithium-ion batteries, are not considered hazardous. They're approved by the EPA for land disposal. Now, we don't do that, we recycle, but it should be reassuring that, the overall classification is one that is not hazardous.
Hey, Michaela, if I can share my screen for a second.
Yeah.
So just as an example, I don't know, can you guys see this
Yep.
graph? Speaking on the smaller scale than what Erin was just describing, but basically all the same components, I thought it'd be useful to just actually look at a big ass steel box that's designed not to burn, sits a little bit away from a building enough that it will contain fire, has built-in fire suppression. This box is safer than your house. I'm just going to make that statement. It's safer than your house. All the electrical components and the built-in protections, the level of monitoring and management wildly exceed the safety of your electrical panel. And I'm sure I could send Jeff Irish to 20 houses and he could find 5 code violations per house. I could even find 3 of them, but take somebody qualified like Jeff. So when we're talking about risks, I've also been in the position of managing 2 megawatts of diesel generators. And in terms of reliability and safety, you know, they have their own issues. One of the big ones being storing a whole bunch of diesel, which in my case cost $100,000 a year just for managing that risk. For diesel generators, that cost tens of thousands of dollars to maintain and basically represented 99.8% reliability when properly maintained, as opposed to 99.99999% reliability of this type of energy storage system. So I'm going to put it out there. There's reason to actually be impatient with this level of concern, and there's reason to be consoled by all of the great work that NYSERDA is doing to, I mean, Candace hit certain pieces of it. For years, New York State has invested in figuring out energy storage, specifically in New York City, relative to the rest of the country, talking with other regulators. Candace, you're too modest. NYSERDA has spent a lot of money figuring out how to deploy energy storage safely and bringing that information to towns. So I'm looking at the tone of some of these questions and feeling like, folks, I know you're not tuned into all of this, but look at this box. The likelihood that this box is going to light up and cause an issue outside of the box, your basement is more dangerous, I guarantee you.
Okay, well, thank you. I mean, any concerns I might have had have been assuaged by our speakers. Hopefully people feel better. And I think we can probably all agree that fossil fuels pose a far bigger threat to our environment, to our health, to our communities than solar plus storage or renewables plus storage ever would, or storage on its own for that matter. So just one more question about concerns regarding storage, and then we'll switch gears a little bit before we have to wrap up. A question about where they're recycled. What is the process for decommissioning a big storage facility, or even, you know, if you're selling your house and you have one of those old ones that Jeff installed, 20 years ago, what happens to those?
So from Glidepath's perspective, we have built into our procurement contracts, the supplier is responsible to safely recycle all the components that can be. There is going to be a larger and larger demand for those kinds of recycling facilities, but there's a lot of valuable components that have residual salvage value in these batteries that can be reclaimed.
And I can answer in the case of the old lead acid battery systems. All of our batteries, almost all of them came from a company called East Penn Battery in Eastern Pennsylvania, and they have a complete life cycle recycling system. Their factory is completely closed looped. In other words, there's no, nothing escapes environmentally from it. And they take back any batteries that we pull out of commission and put them back into that facility, take them apart and recapture all the material.
Great. That's what we like to hear. Okay, this is a nice, simple question, but also a good one. What is the longest amount of time a battery system can store power?
Depends on how big it is and what type of batteries. In the utility scale, the typical, for a long duration battery, the most economical battery duration range is 4 to 6 hours. So for example, a 20 megawatt facility like what we've developed in Hudson Valley, those are either 4 or 6 hour batteries. So that could be measured in megawatt hours. So it could be 80 to 120, 120 to 180 megawatt hours. So it's hard to translate into how long that is for a given house, but.
Yeah, I think the question is a little bit confusing, might mean two things. I think what Erin referred to is the batteries are sized to discharge over, say, 4 to 6 hours in their application. If the battery is left fully charged, lithium ion batteries will hold their charge typically for years. So they're not like car batteries, for example, where, you know, if you don't charge your car up over or run it for 3 months, the battery's dead. They're not at all like that. The leakage currents are very low in lithium ion battery systems, so it's years.
Okay, well, I guess that wasn't such a simple question after all. Okay, here's one more complicated one, and then unless there's, you know, a burning desire to keep going, I don't want to keep our speakers too much longer. But it's great that there's so much interest in this topic. Okay, have any utilities on the mainland, I think this was in reference to what's happening on Hawaii, begun to control their customers' energy storage systems to provide grid services? How far has HECO gotten with this? Are they paying customers fairly if they take some of their stored electricity?
Yeah, Green Mountain Electric is doing that in Vermont.
Can you talk a little bit about, like, explain it to the rest of us who might not understand what that's all about?
Yeah, I could do it, or Tom, since you're in Vermont, I'll give a first swing. What Green Mountain has done is they've implemented a program where they can send a signal to residential batteries, to people who have signed up to the program, and they can pull energy from those batteries. And so they've done that very successfully in times of high peak demand, such as like a hot summer afternoon when the load peaks. And they've reportedly saved millions of dollars by doing that, as opposed to, say, purchasing high cost peak power from places like Hydro-Quebec, or else turning on a natural gas peaker station.
Yeah, thanks for bringing that up, Jeff. I mean, I'm going to back up to a tiny bit. So the batteries are very controllable. The computers that control the batteries are super smart, and we can communicate with them, whether they be in residences, commercial establishments, or attached to the grid, the way Glidepath has developed some projects. How we use that, how we need to use that, the most effective ways to use that is a whole bunch of potential use cases. So in South Australia, Tesla deployed a very large battery, one of the largest in the world, to provide a bunch of grid services. And the grid saved tens of millions of dollars. And the owners of the battery made a bunch of money by displacing more expensive ways of providing those services. What HECO has done, and a little generalizing away from that a little bit, typically, if a battery is going to be participating in, we'll just use the term, a virtual power plant, so controlling a source of power being a dispersed set of batteries, and say, you got 100 houses, they all have batteries. We turn them on, we turn some of them on, depending on what circuits they're connected to. That's a really useful capability, and there's no real limit on how that happens. It becomes an economic deal. What I think the market trend is going to be more and more is third-party entities basically going to the owners of batteries, or as Sunrun, I believe, is one of the folks, right, Jeff? They're actually promoting batteries on the basis of, hey, if you buy the battery, we will go into the market and use your battery a little bit to pay you some money. So that's, you know, a market play where it becomes an incentive to have energy storage. And one of our questioners asked about, what are the advantages of having energy storage? People apply lots of different views to what an advantage is, but there's an increasing likelihood that even residential scale energy storage will have a recognized value for the owner of that energy storage system. And the other thing that Green Mountain Power did was they actually bought and own batteries and have deployed a bunch of those at certain residences that were very expensive to maintain as part of the grid, and basically made a lease deal for those residences and said, look, we're going to disconnect you to the grid, but we're going to give you electric service by deploying this battery. And that's actually worked out really well for a bunch of those homeowners. So we can own the energy storage in lots of different ways. We can take advantage of controlling it to deal with the grid at the transmission and distribution level. And we can deal with the distribution grid, the wires that connect to our houses and businesses, and support that and create some efficiencies and what it costs all of us collectively as folks connected to the grid paying bills by having dispersed sets of batteries interact with that last mile of grid in ways that save everybody money. I mean, that's what we've got to be aiming toward, is economics as a validation of a more efficient system, right?
Amen. And one other kind of more future-oriented question to end us on, related to EVs. How likely is it that New York State is going to incorporate electric vehicles into the system, into the grid for peak times? Anybody want to comment on how that's going to work, when they think that's going to become more of a reality? I know there's been talk of using like electric school buses for peak summer storage. So yeah, who wants to take that one on?
I'll speak to it since I brought up electric school buses as an example. Right now, if I sell you a car and it's an electric car and I provide a warranty, it's an economic warranty issue for you to then take that car and plug it into the grid, if you will. Let's just skip over some details there, and use it as a source of energy. That's not the basis on which I'm selling you the car. And so when you buy an electric car that comes advertised as make money by plugging your car into the grid, that's when it will be a reality. New York State doesn't get to make that call. It's the manufacturers of vehicles that will allow or not allow, by pain of you just lost your warranty, which you probably don't want to wipe out your warranty by misusing something that you bought in general, especially with something expensive like a car. So the technical capability and the economic likelihood, there's a big gap there. Now, school buses and transit buses are different. Number one, they're big batteries. Number two, they're operating on a somewhat different level. They have more significance potentially to the grid. If I plug in 10 school buses to DC fast chargers, that's 0.5 megawatt of demand the second all those chargers kick on. And it's potentially most of 0.5 megawatt that I could inject into the grid. So that's something we're looking at as much more realistic, and at least Proterra, one of the transit bus manufacturers, more than school buses, but they have a school bus play. They are saying we're going to warranty vehicle to grid. I don't think it's actually been done yet, but the folks making the vehicle will allow you to connect it to the grid or not. New York State will applaud and be on the sideline of that decision.
Okay, thank you for that distinction and explanation, Tom. Anybody else want to have a last word on this, or anything else that we might have missed? Usually I have Michaela helping me weed through all of the questions, but her mic is not behaving. So hopefully we didn't skip over anybody's, and we will, as always, copy the questions into a Google Doc and send them around and make sure that we provide answers so that everybody comes away from this really feeling like you got what you wanted to get out of it. Hopefully you learned a lot. And yeah, any last words from our presenters before I just briefly mention our upcoming teach-in next week? Okay, so thank you all so much. That was fantastic. And next week, we will be focusing on the gas proceeding at the PSC on Monday, the 18th at 1 p.m. I believe, right? 1 p.m., Michaela? Yep, okay, 1 p.m. again, same bat time, same bat place, no. And Radina Falova from PACE Climate will be coming and talking about that proceeding, how you can participate, how we're gonna get off natural gas with how we heat our buildings. And so another very important topic in the transition off fossil fuels. So please join us and our friends at Renewable Heat Now for that on Monday at 1 o'clock. We'll include that in a follow-up email. And then we've got a couple of more webinars the following week on solar and jobs and workforce development. So look out for those. And thanks again for being a part of this, for all of your interest in this transition, and keep up the great work and the awesome questions and participating. And let us know if there's any topic that you want us to feature on a future online teach-in. We'd love to hear what you're really interested in learning about. So thanks again, everybody. Be well, be healthy, and we'll see you soon.